Alrighty. Good morning, everybody, and welcome back to Real Analysis. Hope you all had a good spring break, that you got to travel somewhere and for the last week out of class. And
I just want to say that I missed hearing his introduction.
Dr. Webster.
It was a beautiful thing to hear.
Thank you, Dr. Webster. You're wrecking my joke. Okay, so, apologize for being out the last week, but I am feeling a lot better. Hope you all watch the videos for today, and with that, let's get here underway. The for today is we're going to talk about cardinality, which is a fancy mathematical word that means size. So today, in other words, and next week, we're going to be focusing on how can you compare the size of sets, especially focusing on the size of two infinite sets. My next office hours are on Monday, 9 and at 1. As far as homework goes, homework 2, which has been up for a few days now, I decided is going to be due next week on Wednesday. Decided not to make it due Monday because I want to give you all the opportunity to have a couple office hour days. You can come ask me if you have any questions. But we'll be due Wednesday. Also, no mistakes journal due because obvious reasons. And that was your first mistake. But we'll pick that up the following week again. I've not graded basically anything yet, but I would hope to get your homework ones back. Probably won't be done on Monday, but by Wednesday next week. So, either questions or comments before we get started for today? Yes?
I just have a question about something that I couldn't really see on the board or just wasn't familiar with. For the class last week, or on the 26th, you talked about the one function, i.e.
F of A1 equals F of A2.
Is this supposed to be such that?
Let me see. If F of 1 equals F of A2 or something. That was like an F period.
Okay, that was an F. Okay, thank you.
Question. What would a mathematician call a couple of positions?
A couple of positions.
Mathematician would call a couple of positions, Lily? A paradox.
I didn't want to say punchline.
That's okay. Well, as long as you didn't blurt it out early. Let everybody to stew on it for a second. Okay, so today we are starting a new practice session.
I'm sure they would have enjoyed one of the songs we sang at opera.
And So in order to talk about the size, compare the size of infinite sets, we need to use kind of the notions I talked about in my last video of having functions that are one-to-one and or onto. So before we jump into that, a bit of quick review. Let's say I wanted to define a function from the rationals to the integers, where I define f of a over b, we take in a fraction, the form a over b, and we map it to its numerator. I would like to determine if this function is one-to-one and or onto. So first of all, as just a little bit of an example, what would we get if we plugged in 1/6 into this function?
You get one.
Incorrect. Clearly, you would get 2. Three would have been also correct. Also, Negative 100 would have also been correct. Dr. Gerstle, what have you thrown in our laps? Okay, so I wanted to do, so I haven't had a chance to like try and trick you all week. So this is not actually a function. I can't ask if this is one-to-one or not to, because this isn't even a function. Because a function says it has to be a way of taking every element in the first set and map each element here to a single element here. Well, technically, I could take a rational number and map it to infinitely many integers. In fact, well, I can't map it to 0, but I can map it to any other integer I wanted to by just changing the form of our rational number. But that's not a good function, because a good function behaves so that no matter how you write your input, it should always map to the exact same output. There shouldn't be a way of rewriting 1/6 so that it maps to something else. So let's not do this. Let's say we want a function from the rationals to the integers, and I want f of a over b. You take the reciprocal and square it. And this is actually the one I want to determine if this is one-to-one or onto. I fooled you once again. This is also not a function. Because if I tried plugging in the rational number 0, sad times would occur. I'd have to divide by 0. I'm going to put a little x next to the q. The x here just means excluding 0. And now we have something that is actually a function. It takes in a non-zero rational number, it flips it around, takes the reciprocal, and then squares that. And this is a function that's not dependent on how you write a over b. If I plugged in 1/6 versus 2/12 or negative 100 over 600, or negative 600, it would all lead to the same result every time for this one. So first of all, is this function one-to-one? Meaning, is it always going to be the case that no two inputs map to the same output? Or is it possible to have two different rational numbers that evaluate to the same result in the end? What do you all think? Actually, you know what? I'm going to make this an exercise. I want you to take a minute or two here, talk with your neighbors, see if you can determine, first of all, is this function one-to-one, meaning no two inputs can map to the same output, and also, is it onto, meaning, also, I have to do this now, because technically this is not always going to give integer outputs. Is this also going to be an onto function, meaning can every rational number be written as an output of this function? Or is there some element in the codomain, meaning some rational number that is not in the range? Meaning, is it going to be the case that some element here doesn't get mapped to by anything in the original set? Go ahead and take a minute or two and think about this with your neighbors, and then we will come back together.
I'll tell you that soon.
But both of them could be negative or positive, and that's the same thing. You could either choose one.
Because if, like you said,
Not exactly.
Hey,
assume
probably
A and B
but
is
let's see. Caught up on things.
I still think you're not gonna get the same exact answer.
Great, I will be busy after this today. So I think we have access to over the weekend all the old
That's what I think.
Let's try and maybe schedule a meeting time or something on Monday or Tuesday.
Either one or both of the variables can change.
Because I
Wait, what
couldn't
did
think
you
of
do?
possible.
Squared over a squared.
The last couple
Yeah.
classes, because I was just on how's that with those last week? There's a couple videos also that are unlisted that I could send
Might
to
get
you.
be able to take any like do
That keeps asking us to send it to you, but I didn't
the
record
first
it.
two
Or the
25
first couple
times.
classes, so.
I don't know what that would be.
Okay, I have the whole package and their solutions up on Canvas, so I encourage you to look at that and
That
then
makes sense.
let's maybe schedule time Monday or Tuesday to
You could
meet
have
up.
A,
No, is it not?
B, and C, and D, but still.
Awesome. Welcome to the class.
What do you think?
When you take the square root, you have to
Take
put
no.
plus or
You can
minus.
just rudely discard it.
Okay. And then it's either A equals C or A equals negative C.
They came from there.
Oh.
D, or B and D would equal each other, or they equal each other's negatives.
So they would.
Or no.
Okay, let's come back together.
Alright, well, we got one.
So, first of all, let's look at one-to-one. Is this a one-to-one function? Meaning, is it always going to be the case that no two inputs will map to the same output? Or was anybody able to find two different rational numbers here that mapped to the same thing? Laura?
1/2 and -1/2.
Okay, what do we get if we take f of positive a half? See, we get 2 over 1 squared, which is 4. And if we take f of -1/2, that would give us -2 squared, which is also 4. But -1/2 is not equal to positive 1/2. Uh-oh, SpaghettiOs. What does that tell us?
This isn't 1/1.
Yeah, this is not one-to-one. Because one-to-one would require any two different things here to map to two different things here. But Laura was able to find a pair of two different rational numbers, plus or minus a half, that mapped to the same output in the codomain of 4. So since that happened, this is not a one-to-one function. How about onto? Is every single rational number getting mapped to by something over here? Tavio, I see you shaking your head.
Well, sorry about that. No, you're never going to get any of the negative rational numbers, and you're also not going to get 0. The negative issue is probably more significant.
Why not? Why can't we get anything negative?
Because whenever you square something, whether you're squaring a positive number or a negative number, you're going to end up with another positive number.
Oh, gadzooks! We know for any integers a and b that b squared over a squared is greater than 0. Thus, we could say something like, Tavio, give me your favorite negative number.
Oh, jeez. That's a lot of pressure.
Give me a negative number.
Okay, -1.
-1, okay. Asking the tough questions here. We could say that -1 is certainly going to be in the codomain of our function. Because our codomain here is just q. But -1 will not be in the range of our function. Because -1 cannot possibly be an output because all of our outputs are going to be strictly positive. Dr. Gerstle, can it be 0? No. I also agree with Tavia that we can't get 0 as an output because if b is 0, that would mean we plugged in something divided by 0 to start. And don't divide by 0, kids. So, thus this function is not onto as well. Because if it was onto, then every element in the codomain should also be in the range. But we found something -1, or really any negative number or 0 would have worked, that is in the codomain, but not in the range. Questions or comments about this? Okay, groovy. So that was a quick little review from last video. The reason why I brought this up is we need these ideas to talk about sets being the same size or having the same cardinality. So first of all, a couple definitions. I'm going to say that a one-to-one correspondence and if you see me write this out, you're probably going to see me write 1-1 for one-to-one. If you see me write it out on the board, it's just a function that is both one-to-one and onto. If you've taken it, depending on what classes you've taken, you may have also heard the word bijection be used to refer to a function that's one-to-one and onto. That's also equally valid. I'm going to go with one-to-one correspondence because that's what our book uses. But if you prefer to use bijection or epimonomorphism, well, don't use that one because that's implying homomorphism properties that we don't have. You use bijection or one-to-one correspondence. And if a one-to-one correspondence F from a set A to a set B exists, we say that A and B have the same cardinality. And in that case, the notation we use to say that two sets have the same cardinality, the notation that the book uses is to say A tilde B. So the notation that I kind of prefer to use is putting these vertical bars on either side of our sets to say that the cardinality of A equals cardinality of B. And cardinality, which as I said at the start of the class is a fancy word for size, this is going to give us a formal way to compare the size of two different sets. That they're going to have the same size if we can find a function between them that is both one-to-one and onto. Let's do an example. So let's say we had two different sets that we wanted to show were the same size or had shared a cardinality with this definition. Set A is going to be the set of all letters in the English alphabet. And a set T, which is going to be the set of all natural numbers, 1, 2, 3, all the way up to 26. What I would like to do is to find a function that goes from A to T, in other words, a function that takes in letters in the alphabet and spits out integers from 1 to 26 in a way that is both one-to-one and onto. In other words, no two letters map to the same number, and every number gets mapped to by something. What would be a way that we could do that? A way to take in letters and spit out numbers from 1 to 26. Yeah,
is there a way that you could like take the index of an element and set A map that?
Take the index of an element. Oh yeah. I have to start indexing at 1. Is that okay? We're not starting at 0.
Yeah, that's fine.
So we're not going from 0 to 25. I don't want to freak you out here.
Okay. Thank you.
What Alex said in computer science lingo is basically saying take a letter in the alphabet, like A, and say A is the first letter of the alphabet. So we're going to map A to 1. B is the second letter in the alphabet. We're going to map B to 2, and then et cetera, et cetera. So in other words, we kind of write this out. I think Alex has proposed this map right here. Where A is going to map to 1, B is going to map to 2, C is going to map to 3, etc., Y maps to 25, Z maps to 26. Is this function one-to-one? I think so. Doesn't look like any integer here is getting mapped to by multiple letters. Is it onto? I mean, does every integer get mapped to? Yeah, I think
Okay, for that particular set, then maybe it will be onto, but if you consider all integers, probably more.
ooh, if we wanted to map, if we wanted to try this map from the set A to the set of every integer, I think that would be very not onto. We
Yeah.
tried that. Yeah. So if we tweak this a little bit, that would be saying, ooh, no, because 26 letters, infinitely many integers. I don't think you can make them all match up nicely.
Are we assuming that the English alphabet, capital A is the same as lowercase a?
Yes.
I
A is A.
think it would make more sense just to deal with the lowercase because the name of the set is capital A. Yeah, I'll confuse people.
So this does turn out to also be onto. And I think, Alex, the indexing function that you have proposed does work as a one-to-one correspondence in this way.
Just want to be sure.
So we can say F is one-to-one and onto. And that will tell us then that the set A has the same cardinality as the set. They have the same size.
So the way we show this is just by writing it out.
That's certainly a way to do it. We could have written this out in a formula as well. Said f of alpha is the index of alpha in the alphabet. Just written it out with like sort of a formula that way. I have to go to the Greek alphabet because I don't want to use any single letter here. I want a generalizable variable. But that would certainly be another way that we could write that out as well. I wanted to do it this way so we could kind of easily see like the visual relationship between the two, but that by no means is the only way to do it. So here's a question. Let's say A and B are two different finite sets. What has to be true about A and B if A and B have the same cardinality? How could we sort of fill in the blank for talking about two sets with, like, say, 12 elements? Or a set with 15 and a set with 20 elements? What would have to be true about your two sets in order to have a one-to-one onto function between them, do you think? Lily?
They need to have the same number of elements.
It's going to be the case for finite sets, they just have to have the same number of elements.
Do the elements of A all have to be unique and the elements of B all have to be unique?
Yes, but that's kind of assumed whenever you're talking about sets. That like
Oh, okay.
we're not looking at multi-sets in this class. We're not yet looking at multi-sets in this class. So I have a question. Why do I have to, so if A and B have the same number of elements, I claim you can always form a one-to-one correspondence between them by just saying, map the first element in A to the first element in B, second element in A to second element in B, third element in A, third element in B, last element in A to the last element in B. What goes wrong if one of them has more or fewer elements. So let's say we flip the page here. Let's say that you're looking at a set A with k elements, a set B with n elements, and we're looking at the case where n is greater than k, meaning our second set has more elements than the first set. So with a quick little example, we could say something like this. Why can't we form a one-to-one correspondence going from A to B in this case? What would go wrong if we tried to make a function going from A to B that was one-to-one and onto?
You can either pick it to be one-to-one or onto, because you can either map both elements in A to any two elements in B, in which case it wouldn't be onto. Or you can map one element in A to two elements in B, in which case it wouldn't be one-to-one.
Can we map an element in A, a single element in A to multiple elements in B? I don't think so, because I don't think it would be a function if it did that. In a function between two sets, you always have to map a single element in the first set can only map to one element in the second set. So, but I like your the first explanation though. So, what property can a function going from A to B here not possibly have? Really? It can't be onto, because no matter what I mapped 1 to, let's say I mapped 1 to 1, let's say I mapped, I don't know, 2 to 3, there's just too many elements in B in order to have each of them get mapped to by something in A. And so I think in this case, where the second set has more elements, we can say map from A to B can't possibly be onto. It may or may not be one-to-one. This one's one-to-one. If I mapped both elements in A to say the same thing in B, like 2, then it would not be one-to-one. But in this case, no matter how hard we try, it's impossible to form an onto function from a smaller set to a bigger set.
So when we talk about one-to-one, we mean that every element in A has a corresponding value in B?
That has to be true for every function. For one-to-one, it needs to be unique, meaning you can't have, so something, like if I had done this, this would not be one-to-one because there's multiple elements in A that are mapping to the same output in B. One-to-one just means everything in A maps to a different or a unique element in B. What if we have our first set be the bigger set? What would go wrong if we tried to make a one-to-one correspondence from this A to this B? If any, no?
Can't be one-to-one,
Why not?
because two numbers would match to like one number, and A would match to one number in B.
Yeah, no matter how hard we tried to make this one-to-one, we have something like, all right, let's map, 1 to 2, because I'm feeling whimsical. 2 can map to 1, and then 3 can map to, there's nothing left for 3 to map to, unless we have a repeat. If you've ever heard of something in math called the pigeonhole principle, the pigeonhole principle basically says if I have, say, 5 objects, and I want to put them into, say, 3 different slots, there's no way to do that without repeating the slots at least once. It's like the first 3 objects could go into unique slots, but then the last 2, you have to end up repeating eventually. And that's what happens here. There's no way for a function from a bigger set to a smaller set to be one-to-one. And so if we're looking at 2 different finite sets, and we want to say, these two sets have the same number of elements, or if they have the same cardinality, meaning there's a one-to-one and onto function between them, in order to be onto, the second set can't be bigger. In order to be one-to-one, the first set can't be bigger. So if we want something that's one-to-one and onto, your two sets have to have the same number of elements. Neither one can be bigger or smaller than the other one. Questions or comments? Yes?
Just to clarify though, this doesn't necessarily mean. So if they have the same number of elements, they have the same cardinality.
Correct.
Is that an if and only if statement?
Mhm.
So it works the other way as well.
It does as well. If they have the same if they have the same number of elements, then there has to be a one-to-one correspondence also, because you could just map first in A to the first element in B, second in A to the second element in B, and so on.
So there just has to exist a function. It doesn't necessarily have to be like the function that you're working with.
Correct. When we say that two sets are have the same cardinality if there exists a one-to-one correspondence, that doesn't mean there has to be every function is a one-to-one correspondence. So for instance, with this a and this t, I could very easily make a function that is not a one-to-one correspondence here. Let's say I wanted to map A maps to 1, B maps to 1, C maps to 1, D maps to 1, E maps to 1, Y maps to 1, Z maps 25. That would be a function that is very much not one-to-one, because lots of things are mapping to 1 here. It's also very much not onto, because 1 and 25 are the only integers here getting mapped to. This is very much not a one-to-one correspondence. But we can still say that A and T have the same cardinality, because at least one function from A to T is a one-to-one correspondence. Not all of them have to be, you just need to be able to find one of them. In fact, in this case, there would be 26 factorial different one-to-one correspondences we could choose from, potentially. Dr. Gerstel, I don't need one-to-one onto functions to tell me if two sets have the same size. You give me a set of 10 marbles and a set of 10 pieces of bacon, I know that they're the same number. Thank you very much, without having to think of one-to-one and onto things. So why are we bothering to talk about this? The reason why,
Because we're going to be dealing with infinity, different sizes of infinity.
yeah, the reason why is because this definition of cardinality can be used to compare infinite sets just as well as it can finite sets. Whereas if I tried to say, all right, I have 10 pieces of bacon and 10 marbles, it's easy to tell if they are the same set. Whereas if I were to tell you, let's look at the set of all rational numbers and the set of all irrational numbers. Which of these is a bigger set? Or are these sets the same size? It's a tougher question. You can't just say like, oh, I see the same number of things here as I do here, therefore they're the same size. It's a little bit more vague. And this is going to be used to be our definition of these infinite sets are the same size. Our definition is going to be two infinite sets have the same size if they have the same cardinality, meaning there exists a one-to-one correspondence between them. So let's do an example. I claim that the integers and the natural numbers have the same cardinality. Meaning I claim I can find a one-to-one and onto function going from the integers to the natural numbers. How can we do that? Would be a way to find a function f going starting with the set of all integers, going to the set of all natural numbers in a way that is both one-to-one and onto. Billy, is that at hand?
Maybe. Well,
Maybe
I'm calling on you, Lily, what do you think?
something like, a squared plus 1 maybe?
Ooh, just take an integer and map it to that integer squared plus 1?
Yeah.
What's going to map to 3? I was going to say, it'd have to be like square root of 2, which is not an integer.
I don't
It's
know.
a good idea. Good idea, but I don't think that quite works. Rachel, what do you think?
Take any integer and maps it to its absolute value.
Ooh, okay. So take f of x equals absolute value of x.
Mhm.
That would certainly be a way to take any integer and map it to a natural number. What would 3 map to?
To 3.
What would negative 3 map to?
3.
Is that 1 to 1?
Oh no.
Like I said, that is a function from the integers to natural numbers, but unfortunately, I don't think that one's going to, and that one would be on 2, but I don't think it's going to be 1 to 1.
Yeah, okay.
Dan?
If it's a negative number, multiply it by -2. If it's a positive number, multiply it by 2. I know. But
So that sounds like take 2 times the absolute value. I think would be the net effect of doing that.
that's a good idea. That was close.
Laura?
So I don't really know a mathematical way of saying this, but suppose you take a positive number and you multiply that by 2, it'll map to what multiplies by 2. And then if you have a negative number, you do that multiplied by 2 plus 1.
If you have a negative number, map it to 2.
Or no, or times negative 2 plus 1. So it's absolute value times 2 plus 1.
Alright, tell me what these are all going to map to.
So I would say 0, since that's kind of weird.
0 cannot map.
0 maps to 1.
Okay.
1 maps to 2. 2 maps to 4. 3 maps to 6. 4 maps to 8. Now if you put up some negative numbers there, you have -1.
Alright, let's start over.
What? Well, -1 then has maps to 3. Yeah.
Okay, so -1 maps to 3.
1 maps to 2. -2 maps to 5. 2 maps to 4. -3 maps to 7. 3 maps to 6.
And then, so each time you go from positive to negative, you, you increase by 3 and then go down by 1?
You could say that. Well, the way I thought of it was you take the absolute value of a negative, multiply it by 2, and then add 1.
Okay, so interesting. So it sounds like, Laura, what you have is a way of mapping positive integers to even natural numbers other than 0. And your negative integers are going to map to odd natural numbers. Is that 1 to 1 and onto? I think that works. Yeah, that's actually slightly different, but very similar to what I had in mind, which is something that would map all of the even integers to all the positive integers to even natural numbers, all the negative integers to odd natural numbers, and then 0 just has to map somewhere. But that would certainly be a way of finding a function from the integers to the natural numbers that is both 1 to 1 and onto. And by the way, there's not really a way to do this other than that's not sort of janky like this. There's not like a nice formula, I think, that makes this very easy and straightforward. But that is a way of saying that the integers in the natural numbers have the same size. They have the same cardinality. That's kind of weird. Why is that weird?
I guess it's saying that infinity times 2 is equal to infinity.
Yeah, did y'all ever have these like playground arguments as kids where it's like, my power's infinity plus 1, my power's
So
infinity, it's infinity plus infinity. 5 infinity squared. This is sort of giving some indication that if we take that, hey, we have two infinite sets where you could sort of double the number of elements in here and add one, you'll get the number of elements here. Surprise! You haven't actually changed the size at all by doing that. These two infinite sets still have the same size. From the fact that you can have this one-to-one correspondence between your two sets, infinity plus 1 is not any bigger than infinity. Infinity times 2 is not any bigger than infinity. Infinity squared is not any bigger than infinity. 2 to the power of infinity is actually bigger than infinity, but that's a topic for next week. So moral of the story is counterintuitive stuff happens when we talk about the size of infinite sets. If I were to say start with a set with 10 elements and I wanted to double the amount of things in that set and then add 1, that set's getting bigger. Set with 10 elements versus 21 elements is not the same size. But starting with all the natural numbers is sort of doubling that by taking them in their negatives, and adding 1, or adding in 0, is not actually changing the size of the infinite set in any way. Very counterintuitive, but something that kind of follows mathematically from this result. Questions or comments? And Lily, you're up here trying to think of something to off the wall question to try and stump me here.
I have another question. Not a question, but how, for instance, I say f of x is x absolute plus 1.
Say that again?
The absolute value of x plus 1.
Like that?
Mm-hmm. Because we can start from 0, and then you'll have 1. And then take 1, you'll have 2. And then negative you can...
I think that,
that's a
Yeah, it's still
problem.
not
Yeah,
gonna
that's
be-
the problem.
I was going to say, I think that's still not going to be 1-to-1, unfortunately.
Yeah,
It's on 2, and it does give a function from the integers to the natural numbers.
yeah.
It just doesn't do it in a
Yeah.
1-to-1 way.
Yeah, that's right, that's right.
So this is kind of saying that infinity is equal to 2 times infinity. But if we were,
Intuitively, yes. We're going to be more formal about this next week, just so you all know, but for today I'll allow these sorts of statements.
okay. So if we were to divide all the natural numbers by all the integers, wouldn't that equal 2? Well, I guess 1/2.
Wait, what?
Um,
If we divide all the natural numbers by all the integers, we get a...
the number of
Oh,
natural numbers by the number of integers, wouldn't we get 1/2?
how are you defining division? Of
So I'm
infinite
thinking,
numbers.
I'm thinking of like with limits, how
Ooh.
as x goes to infinity, then you can get like a number.
You could say
fraction.
something like, you could certainly say something like that.
So can't we say that one infinity is bigger or smaller by another infinity according to that logic?
How does this apply to two sets? You're taking a limit as n goes to infinity. Are you changing the size of your set? Are you adding elements into it or something?
Well, let's say n doesn't go to infinity, but n goes to the number of elements in an infinite set.
I was thinking along the lines of limits too, where you have like two values and you have like n approaches infinity and p approaches to infinity. Then what do you get?
You get a right mess. Y'all are thinking ahead, so we're going to be talking a lot about limits in this class. I think that's like a couple weeks out, but y'all are asking really good questions, and my answer is mainly along the line. The short answer for now is you can't do that. With p goes to 2 times infinity. But I get what you're trying to say, and you're into it, and I love that you're trying to break your intuition. Our definitions are not going to allow for something like that.
this, if both of these are infinite sets, then in order to like fully prove this, wouldn't we have to go to, I mean, sure, infinity doesn't have an end, but when we go on forever, and therefore to prove this, we'd have to prove this one-to-one correspondence forever.
Hey Laurie, you gonna prove this forever for us?
No.
So if we wanted to prove this formally, we probably have to come up with a formula, something like f of x equals 1 if x equals 0, negative 2n plus 1 if x is less than 0, and 2n if x is greater than 0. And then we could use a formula like this to actually like write a more formal proof of this rather than z. And notice as this goes on, nothing's going to repeat and everything's going to be hit. We could certainly make it a little more formal, and that's how we would do it. Using formula. I don't really feel like writing that proof out there. That's how you would. All right, next page. Packet, 3 sets. The interval of all real numbers from 0 to 1, the set of all even natural numbers, and the set of all rational numbers. My challenge to you all, working in small groups, as usual, see if you can determine which of these do you think are going to have the same cardinality as the natural numbers. The integers did, so maybe some of these sets do. And which of these do you think are not going to have the same cardinality as natural numbers? Go ahead and talk to your neighbors, and I want you to think about this for a few minutes. See what you can find. Say what?
The first one is good.
Yep. Doesn't change number of elements.
Yes.
Let me put it this way. It doesn't change the cardinality. It doesn't change the size of the set. We can't really talk about size as being number of elements when we're talking about infinite sets. But the size doesn't change. That is correct.
I think all natural numbers, the inverse of it.
Are you doing
The second one is
Well, our end game here is trying to see compare the set of rationals and the set of reals and see do those have the same size.
Wait, so why is your one?
So let's use that they're at least the same.
well,
In brief,
So I mean,
Okay, yeah.
What are the real numbers?
so this would just go into.
But I'm just showing you the rational.
Yeah, when you just multiply it by 2 like this.
Oh, okay, so then for natural numbers.
And all the real numbers.
So why are we saying that?
Oh, because basis is like symmetric for every single.
here we go.
Tommy, why don't you explain it?
No, you
That's not.
explained it to me though.
Oh,
That's why I know.
Okay.
Yeah, anytime I give you an interval using expert notation, unless I say otherwise, it's going to
It's
be
basically like infinite.
all reals.
Yeah.
I assume like zero.
if you.
All real numbers have such that 0 is equal to
Because
x plus 3.
like this one.
Zero one has
What's the natural
all the negative.
Basically, this base is 0 to 1.
I'll go over it in class. The second one is half.
Your probability.
That's everything. That's all reals. Anytime I give you an interval with that sort of notation, assume it's an interval of all real numbers.
Just basically doubling it.
That's a really bad proof, but it's technically right.
What's a really bad proof of technically right?
This is what I wrote my
So you
computer
take out
science
the-
seconds.
Yeah, you're exactly right. You just
Inverse
multiply
of
the
natural numbers is always
Yeah.
but,
This is true.
and then you have the, in between each of those, you find another
I can't prove
infinite set of particular numbers.
Right.
It's really bad, but I know it's true.
Your argument,
Here's the thing, the rational is
your argument does not work.
The rational is
For reasons we'll talk about next week. I don't want to get into why so much now, but basically, just because you can remove a copy of something that's the same size as a natural number, even though you can remove that an infinite number of times, that still doesn't necessarily work. Therefore, because the union of because the countable union of countable sets is still countable,
Yeah.
is the technical answer, which is something we're going to talk a lot about next week.
Well, shucks.
It's a good idea. I'm glad you're
Infinite
creatively
amount of
there,
infinity.
but that's not going to quite work.
Given any real number,
I like that too.
you can make a rational number put in between them.
Well,
That seems to hint to me that there's a similar
But you can
situation.
also do the vice versa. Wait, guys, are we mapping n?
Are you saying that for
No.
numbers? Is that what you're doing?
No, we're saying that they're sharing.
That's what I was-
I guess either way.
It would have to map.
Oh, I was saying I can see some flowers.
You guys have on to, there to be on to.
Huh?
Let's say it's that have to back on. Yeah, so it doesn't matter which one.
Yeah, you can map it.
It kind of does, because you can't go from 2
Okay,
and
I have a
n.
different one.
Literally. Hey, I figured it out.
Okay.
Oh wait, that's an interesting one though.
So in theory, there is some natural
No.
numbers.
I'm going to let you think about this more. I need to.
They're all
Minus one. Yes. Yes.
Okay. Can I have everybody's attention?
Okay, so
We are out of time for today, unfortunately. But you all are having some great thoughts, I'm hearing, as I walk around the classroom. When we come back on Monday, we are going to talk about each of these and then see what sorts of more formal, and next week we'll be a little bit more formal and try and make, see what sorts of sets of infinite numbers can we prove have the same size, and how can we prove two infinite sets, say, have different sizes. With that in mind, hope you all have a good weekend, and I will see you all on, what is today, Friday? I'll see you all on Monday. Have a good weekend, post spring break weekend.
Does this mean we won't have this